Hello everybody, welcome back to another episode of the problem solving series. In today's video we're going to be covering moment of inertia and I'm going to cover center of mass in this video as well, just because the equations for each of them are kind of similar, so I think it makes sense to just pair them together. Before we can go on and move into the next three or four concepts, we just need to cover the equations for moment of inertia and the concept and what that means. So without further ado, let's get into it. Okay, so up until this point, we've kind of been starting to introduce you guys to this idea of we have all of these quantities linearly that we've been working with, kinematics, momentum, energy, forces, so on and so forth. And now all of a sudden we're now transferring over into looking at them in these rotational frames as well. So far I think I've only introduced to you guys really looking at the rotational kinematics, so comparing the linear quantities to the angular quantities. But essentially every single concept that we've covered thus far that does operate linearly does have a rotational analog. And moment of inertia is going to be the rotational analog for mass. So where, theta is our angular position, omega is our angular velocity, and alpha is our angular acceleration, our moment of inertia essentially is it involves mass, but it's a little bit more nuanced in that when we're rotating things, we want to take into account how that mass is distributed. We can't just kind of assume everything is a point mass and that the mass is solely centered on one point, which is kind of what we've been doing thus far, but probably nobody told you that that's what we're doing. So, surprise! That's what you were doing. Now we're going to take into account things being extended and having masses in weird places and how that affects how things are going to rotate and how things are going to move. And then also how other physical quantities are affected by this. But again, those are for later. We'll just talk about moment of inertia for now. So moment of inertia is denoted by a capital I, and we write it first as the sum of, so if you have a collection of masses, you write it as the sum of those masses times the distance that they are from whatever point we're looking at rotating about squared. So this will be capital I equals the sum over all the particles indexed by some little I, and then each of those masses times their distances squared. If you are in a calculus-based class, they go a little bit more in depth with just calculating these, not so much in the algebra-based class, because the calculus-based class will switch over that sum into an integral. I'm not going to cover that in this video. This is just for an algebra-based course, but just know that there is that option as well. That being said, for the algebra-based course, they do also give you the moment of inertias for a lot of common shapes. So I will put a graphic of that over me, and you can go ahead and screenshot that. And some of those common shapes are going to be solid sphere, a spherical shell, a hollow cylinder, a solid cylinder, so on and so forth. There's kind of like this table of usual shapes that they give you, and they'll just give you the moment of inertia for that in a calc-based class you would have to derive, or they'll give you the chart, but you should know how to derive that on your own. So for the most part, you'll just be either know which moment of inertia that you have to use, so being able to identify the shape and then look up in the table which moment of inertia that you need to use. You could have to calculate the moment of inertia from a collection of points. We'll do an example. The first example that we do will be covering that. And then there's also the parallel axis theorem. So the parallel axis theorem states that the moment of inertia for any shape can be written as that is off center. So if you want your shape, I don't have any good shapes. I have a cup, but it's full of coffee. So we'll pretend that this is our cylinder, and typically cylinders are going to rotate around this axis in the center of the cup. But if for some reason you wanted to know the moment of inertia if we rotate around the edge of the cup, that would be equal to the moment of inertia at the center, which would be the one that, say, we would look up in that table that I showed, plus the mass of the object times the distance from center squared. And I will put that up over here as well. Also, just going to take a sip while it's here. So moment of inertia for an algebra-based class doesn't exactly hold water on its own. There's a chance on an exam you could get a question here or there, but more often than not, it's going to be baked into another question where like that's a step along the way before you can solve for what you're looking for. Since it is the analog of mass, and mass comes up in a lot of the equations we have, you could think so mass comes in momentum, kinetic energy, and forces. So that's already three concepts that if you're doing things in the rotational analog, you are going to need to know the moment of inertia for. So that could be something that easily gets kind of baked in along as one of the steps you need to do to solve for something else. Moment of inertias are scalar quantities, so they will just add the way that masses just add. So I'll probably show more examples of exactly what I'm talking about in those other concept videos as I make them, but just to kind of give a general example here, like it's really common to have, say, like a kid sitting on one of those merry-go-rounds and they start off at the edge and you want to know the moment of inertia of the whole system. You take the moment of inertia of a disk and then plus treating the kid as like a point mass plus the moment of inertia of a point mass some distance from 0, which you would take to be the center of the disk. And then kind of in a similar vein, center of mass, depending on the class and kind of the time frame that you're under, sometimes it gets covered, sometimes it just doesn't. But the equation is very similar to moment of inertia. But instead, we're going to be taking so this is going to be in X or in Y. So along a single dimension, the center of mass coordinate is going to be equal to the sum of the individual masses times their distances divided by the total mass of all the particles that you have. So I'll put that up here. Now, center of mass doesn't get baked into the other concepts the same way that moment of inertia does, but it's also not really the most important physics concept that you need to come away with in a physics class. I think that's why, depending on who's teaching and what book you're using, and like if you're running out of time, that is one of the topics that I think kind of just gets pushed to the side. If anything, it would maybe be one question on an exam, maybe a conceptual question. So I would recommend not to go crazy over it, but it is good to know just to get those points and to understand how you calculate the center of mass of an object. So yeah, let's get into our example problems and I'll show you guys how to calculate these things.
For the following configuration, calculate the moment of inertia about the points A, 1, 1 and B, 0, 1. So we've got our masses listed out next to the points on our XY plane. And I'm just going to write out our formula for calculating moment of inertia. That is I is the sum over the individual points that we have, mi/ri squared. So in the first case, we're looking at rotating around this point. So this distance would be 2. This distance would be 2. And then we're going to want to calculate this distance. And since it's a square, we can say that that distance, and I guess maybe I'll label these points 1, 2, 3, and 4. So if we were to plug that into the formula, we're going to have m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. So this will be true for A and B. But for part A, we're going to have r1 equals 0, r2 equal 2, r3 is going to be 2 squared plus 2 squared square root. So just using Pythagorean theorem to solve for that, which is 2.83, and r4 is 2. We can also list out our masses. So m1 is 1, m2 is 2, m3 is 1, and m4 is 2. And then we can plug those into our equation. So I'll call that IA will be 1 times 0 squared plus 2 times 2 squared plus 1 times 2.83 squared plus 2 times 2 squared. And if we add all those together, we get the moment of inertia is equal to 24. Now I'm going to go ahead and try as best as I can to erase these. Our rotation point now being about 0, 0. So for part B, now this is going to be R1, this is going to be R2, this is going to be R3, and this is going to be R4. They'll actually all be the same magnitude. So I'll go down here and just solve for the first one. So R1 is going to be 1 squared plus 1 squared square root, again just using that Pythagorean theorem, and I get 1.41. And then R2 is also going to be equal to that, as is R3 and R4. Our masses are the same. And now for moment of inertia for part B, we'll have 1 times 1.41 squared plus 2 times 1.41 squared plus 1 times 1.41 squared plus 2 times 1.41 squared. And then plugging that all in, I get the moment of inertia around 0.00 to be 12. Oh, and the units for this, kilograms meters squared, kilograms times meters squared. Find the moment of inertia for a rod rotating about one end. So this is going to be our parallel axis theorem example. So we do know, so for parallel axis theorem, we're going to have I equals I center of mass plus d squared, where the distance is going to be, or d is going to be the distance from the center of mass to the point that we're rotating about. So for a rod of length L, we're going to be looking at, instead of center of mass, we're going to be looking at rotating about one end. So this will be d equals L over 2. And looking up in the table of common moment of inertia shapes, we'll have that the I center of mass for a rod is 1/12 ml squared. So we will just go ahead and substitute in 1/12 ml squared plus ml over 2 quantity squared, and then we will simplify this expression. So we'll get a 1/12 ml squared plus a 1/4 1/4 ml squared. So we can pull out an ml squared. We'll get 1/12 plus 1/4 ml squared, which gives us 1/3 ml squared. For the following configuration, calculate the center of mass. So this is the same configuration as in the first example. I didn't specify here, but we're just going to be taking the center of mass with respect to the 0, 0 point. So we're going to be looking at this, and we're going to be, let's write down our center of mass equation. So our x center of mass is the sum of over the particles, the mass of the particles, times the x position, divided by just the sum of the mass. And we get the same expression just with y's for the y center of mass. And we list out, so again, I'll label these 1, 2, 3, and 4. And we'll have y1 equals 1, x1 equals 1, y2 is -1, x2 is 1, y3 is -1, x3 is -1, and then y4 is 1, x4 is -1. And obviously this is m4, m1, oop, that's not the right spot, m1, m2, and m3. So we'll do x center of mass first. So x center of mass is going to be equal m1, x1, m2, x2, m3, x3, plus m4, x4 over m1 plus m2 plus m3 plus m4. And then we'll substitute in. So 1 times 1 plus 2 times 1 plus 1 times -1 plus 2 times -1 all over 1 plus 2 plus 1 plus 2. And we actually, so maybe this wasn't a good example to choose. So this will actually give us our x center of mass being 0. And let's see about the y center of mass. So our y center of mass, m1, y1, m2, y2, m3, y3, m4, y4 over m1 plus m2 plus m3 plus m4. So we'll have 1 times 1 plus 2 times -1 plus 1 times -1 plus 2 times 1 for 1 plus 2 plus 1 plus 2, and this is also going to give us 0. So nothing really spectacular with these results, but just to show you how to use these equations.
Okay, and there you have it. So that is my take on moment of inertia and center of mass. Thank you guys so much for watching, and until next time, happy physicsing. Bye. What is the matter? Oh, please. You gonna say bye to the kiddos? Oh, bye bye, Bubba.